If you can draw a function without lifting your pen, then that function is continuous. So I might have something like this, right? And if I pick two arbitrary points like that, I can say that this function is continuous on the interval a, b. Another kind of continuous function is a piecewise, or, well, it's possibly continuous. So we have a piecewise function, and you'll see what that looks like when you're doing your homework on ALEKs. But if I think of the tax system in Canada, so I've got taxes paid, specifically income taxes, and I've got your salary or your income on the x-axis, it would look something like this. We've got at first, when you start earning money, you actually don't pay any income tax on the first few thousands of dollars that you make. And then your marginal tax rate goes up. And as you get into higher income tax brackets, the additional income that you make gets taxed at a higher marginal rate. And so you end up having this kind of kinky function that looks like that. So as your salary goes up, you move into higher tax brackets. So both these functions look a little bit different, and they have different qualities, but they're both continuous. Now let's move on to the next slide, and we can see here we've got a function we're already familiar with. So we looked at this, and we showed previously that if x is equal to 0, f of x, or the limit as x approaches a of f of x, is going to be equal to 1. And so there was a limit right here. But notice that plug x is equal to 0 into this function, it's undefined. And so there is a hole. There's a hole in our function. So f of x here is discontinuous when x is equal to 0. So there's a hole in this function, and the function is discontinuous when x is equal to 0. If we look at other parts, we could say that, oh yes, this is continuous on the interval say -2, -1, and on the interval say 0.5 to 2. So the function is continuous in different spaces, but it is discontinuous when x is equal to 0. And this is a special kind of discontinuity, and it's called a removable discontinuity. What do we mean when we say it's removable? It means that if we replace x equals to 0 with its limit, we could turn this into a continuous function. So that's what we mean when we say it's removable. It's a removable discontinuity. Remember this function? We showed previously that, maybe I'll draw like a solid dot there and then a hole here. We showed previously that at x equals a, the limit as x approaches a of this function f of x does not exist. And if the limit does not exist at a point, in this case A, at point A, or any point for that matter, if the limit does not exist at a point, then the function is discontinuous at point A. Now, of course, or maybe not of course, on this interval here, if I call this B and C, f of x is continuous here, right? I could draw that without lifting my pen. The limit certainly exists on that space. F of x is continuous on the interval B, C. Now let's get back to the discontinuity that we see right here. This kind of discontinuity is called an irremovable discontinuity. We can't just replace the discontinuity with its value at the limit, because you see that there's this big jump. And we might have, if you look in the Sid Seder textbook, you can see examples of functions that we use, for example, levying taxes, that has jumps in them. And there's nothing you're going to be able to do to try and make this function continuous at the point A. Of course, looking at this function that we have right here, you can see that there's lots of points where this function is perfectly continuous. And so as an economist, if you're only interested in the parts of the curve that are continuous, you don't have to worry about the discontinuity bits. You can just focus your attention on the points where it's continuous. To summarize, this kind of discontinuity that we see right here is an irremovable discontinuity. There's not really any way to get around it. This function has this sort of jump. Here's an example. Take a look at this kind of wild-looking function on a graph and see if you can identify which points are discontinuous. Press pause. When you're ready, press play, and I'll show you the answer. I hope you're able to see that we have three candidates for discontinuity. We have x is equal to -1, x is equal to 1, and x is equal to 3. When x is equal to -1, we have a removable discontinuity. So the function jumps up to y is equal to 2. Now, but we could still replace, if x is equal to -1, we could replace f of x, f of -1, with its limit. So this is a removable discontinuity. Same with x is equal to 1. This is much like the example that we saw with that function ex minus 1 over x. It's a similar situation as that one. Good, I'll just erase that because I don't want you to think that's the actual function. And so x equals 1 is also a removable discontinuity. And then we have another candidate, x equals 3, and we can see that the function jumps up like it did here, but in this case it continues on to the end of the interval that we're looking at, that we're analyzing. And so x equals 3 is a irremovable discontinuity. It's not something that we could easily get rid of with this function without changing the properties of the function itself. Here I am on ALEK's. We've got the same question that you saw on the slides. I'm going to input my answer. So ALEK just wants this, ALEK doesn't care whether it's a irremovable or removable discontinuity. It just wants to know if it's discontinuous at which point. And so I'm just going to list the x values where this function is discontinuous. And so we have -1, and then I'll hit comma, 1, comma, 3. And so we've got -1, 1, and 3. And that looks like all the discontinuities. So I'll hit the check button. Let's see if we have the right answer. And we do. So we got the right answer. And that's how you're going to find discontinuities on a graph. Before we end the topic on continuity, let's just summarize the relationship between continuity and limits. If a function is continuous at point A, then the limit of that function approaching A must exist. So if a function is continuous at a point, that is a sufficient and necessary condition for the limit existing at that point as well. Now if a function has a limit at point A, then f of x may or may not be continuous at point A. So just because a limit exists at point A doesn't necessarily mean that that function is going to be continuous at point A. You're not sure. Having the limit exist is a necessary condition for continuity, but just because the limit exists doesn't necessarily guarantee, it's not sufficient, that the function is continuous at that point. And so this kind of ties it together, and this is just a very sort of general, light introduction to continuity and limits. We'll be using certainly limits later in the course when we start talking about calculus.